Hi, I'm Tanya Atwater. I'm an emeritus professor at UCSB, and I've put together some geology information for you about the islands. What I have right now is a first draft, so I'll make a better one for you guys to have to use in the long term. But anyway, here it goes. You have to start with the plate boundary. You know, living in California, that we live with the San Andreas Fault. Here it is, just offshore of San Francisco, and wraps around. Here's the LA basin. And then it goes down into the Gulf of California. It's the primary plate boundary between the Pacific and North American plates. And here's the really big picture. We were just looking at this part of the plate boundary. That's the San Andreas Fault, and then it goes on down the Gulf of California. Here's the North American plate. If you hold it still, with respect to it, the Pacific plate is moving across the face of the Earth from where it's been formed at the spreading centers to where it's being destroyed at the subduction zones off of Alaska. Here's Alaska, and off of Asia. You can see a small piece of North America has been broken off, and the Pacific is dragging it along. You see, so if you just hold North America still, the Pacific is moving by, and it's dragging all of Baja and the rim of California towards the Aleutians. Well, it's never so simple. Here's the San Andreas we just saw. There's San Francisco. And you can see in Northern California, it's pretty tidy. These are just a few faults, but in Southern California, it's much wider zone. These are onshore, and then the offshore is also full of faults. So it's a very wide shear zone. You can see that in this one, the San Andreas is coming down through here, but this is the edge of the continent way out here. And this part of the continent's all broken up. Looks like it's just been shattered. That's very unusual. Continental edges almost always look like this, continental shelves. That's an unusual thing we're trying to explain. And when we look at the Southern California map, here comes the San Andreas again, along there. Here's the LA basin and Santa Barbara. You can see all those other faults. There's one here, and there are a bunch in the not mapped here. You can also see up here, there are a bunch of east-west faults and east-west mountain ranges. That's really crazy. Almost all the faults along the edge of the continent are approximately parallel to the edge, except right in here, east-west. And the islands are all lined up east-west with the Santa Monica Mountains. So that's a thing we're trying to explain. Here's the explanation for this. All these east-west coastlines and mountain ranges, they all line this block that we call the transverse ranges block. We believe it started out down here up against San Diego, and it's been rotated 110 degrees clockwise by the motion of the Pacific plate. I've made a bunch of animations to try to explain these things, and here's the first one I ever made. You can see here we are again. Here comes the plate boundary, the main one, but then it has all these other faults and lots more than I drew here. And here's the east-west transverse ranges block. So our idea is starting 20 million years ago, as the Pacific was dragging the rim northward, that little piece got caught. It's almost like a log at the edge of the river, one end dragging on the mud and the other end being carried by the current. Here's the bigger view. The Pacific first made contact with North America right off of Southern California here and began to pull off pieces. and it ripped off more pieces. There's our little piece that got snagged. And then later it took off Baja as well. Here's a close-up of that. It's a pretty crazy idea, that rotation, but we're very convinced that it's true. Here's some evidence, just a small bit of the evidence, but my favorite pieces. We can tell from paleomagnetic rotations and from the Poway conglomerate. Okay, first the rotations. Many rocks contain magnetic minerals, and when the rock is formed, that mineral gets frozen into the rock, pointing in the direction of the field at that moment. So if we go back to 20 million years and see how the rocks were magnetized, here's San Diego and Santa Barbara, and then we let it come forward with that, the rotation history goes like this. So most of the rocks around Southern California still point north, but all the rocks that are inside this block, all the older rocks, are magnetized towards the east, as if the North Pole were in the middle of the Atlantic. It's pretty crazy, but it's very well established at this point. This is some data from the thesis of Scott Hornafius, and he just went around sampling and measuring the directions of magnetization of all the rocks and all these dots. And these pie charts show the direction that they're magnetized. He had dates on those rocks, and the older ones were rotated more and the younger ones less, because the piece had already partly rotated around by the time they were formed. Okay, what about this Poway conglomerate? A conglomerate is just a rock made out of other rocks, and there are some really special ones around Southern California. They contain these maroon kind of rocks with white crystals. We call those the Poway clasts because they're quite common in the river sediments at Poway, California. They're very distinct. You don't find rocks that look like that very often, and they're all about 150 million years old. We find these rocks along the coast near San Diego and also in the country behind it on the Channel Islands, and they come from a volcano that erupted here in northern Sonora. Here they are at La Jolla, Torrey Pines. The waves have been eating away at these cliffs, but they're part of a huge delta from a big river. A lot of it is sand and clay that gets washed away, but whenever there are stones in this delta, they end up on the beach. Went on a search one day to find them inland, and it turns out behind Poway, California, east of San Diego, all the houses have rock gardens. Their soil is so full of these stones that a lot of them have just given it up, and they have all these red stones, these maroon stones. So that's here and here. Up in the Channel Islands, this is in Sauces Canyon of Santa Cruz Island. It's a drainage that goes out the west end. And you can see this is part of that same delta. There's some sandstone, but here's a river sediment full of stones. And there they are, the Poway class, same as at San Diego. This is on the beach right near there, on the beach south of Christie's. Here are some animations I made to explain that story. In the Jurassic, 150 million years ago, we had a subduction zone here, and behind it were a bunch of volcanoes erupting. This was the one that made the Poway stones. Then in the Eocene, about 50 million years ago, there was a big river system. The eroded rocks were carried down the river and dropped in a big delta offshore. The river's still there behind Poway, and the delta we saw at La Jolla, but also way up at the Channel Islands. So you know how this story's going to go. If you break up the delta and carry some of it away, and later on, when Baja California gets stolen by the Pacific Plate and dragged away too, we end up with the volcano way down here in Sonoya. But the riverbed and the delta at San Diego and the toes of the delta out on the islands. This was such a crazy distribution. People just, before we had the rotation, people just couldn't figure out how to do it. Here it is, that same block, and it's put a big dent in the coastline, which is a wonderful boon for us because the cold current that comes down from Alaska misses us a lot of the year, and it pulls the water out from the borderland here, much warmer water that's being pulled up. And likewise, big storms in the North Pacific send waves down, but the waves would have to turn around and then turn around again to come to our coast. And furthermore, since the mountains face south, it keeps us warm in the winter. I made a physical model to show this rotation, and you can get a hold of a copy of it if you want. This is the present configuration, and let's find ourselves. There's the Mexican border, Santa Barbara, LA, and San Diego. Here's Baja California and the Gulf. So if you take it back to 18 million years, there's 18 million years ago. Pull Baja still, that's right here, and pull on the Pacific Plate. And starting about 6, let go of Baja because that's when it joined the train. And there we are. Channel Islands are really different from the islands we usually think about in the ocean, like Hawaii or the Galapagos or the Azores. Those ocean islands are the tips of huge volcanoes that were built miles high upon the deep seafloor. Our Channel Islands, it's really different. They're just the tops of jumbled, broken pieces of continental crust. Continental crust extends all the way out to here, and that's just all broken up. Let's see, here's Los Angeles and Ventura. You can see the offshore looks like it's all broken up into chunks, and the islands that are above sea level right now are just the tip tops of those tilted chunks. Up here, this is part of the transverse ranges block that rotated, and these chunks are running into the edge of that, and so lifting these islands up. Now, it is true that there are volcanic rocks on our islands too. The north side of Santa Cruz is mostly volcanic, and Anacapa Island is completely volcanic. But it turns out these volcanic rocks are just skin deep. They're the lavas that poured onto the land surface as the crust was being broken up. The islands share a lot of geology with the geology that we see on land. For example, in the Oligocene, that's about 40 million years ago, sea level lowered and the coastline retreated to the very edge of the continent, and our region became a big floodplain. Here's a painting by John Iwerks of what he imagined it to be. Big meandering river, and there are lots of weird creatures. This is kind of midway through the Cenozoic and the development of mammals. The thing the geologists see most of all is that the rocks are often red. If there's any iron in sedimentary rocks, and if they're under a situation like this where they get wet and dry, they all get rusty. Behind Santa Barbara, this is what they look like. River floodplain, except they've been tipped up, but they're very red. On Highway 33 north of Ojai, really red. All the red sediments that are around in our region, they're all from this time, the Sespi. And when you go to the south side of Santa Rosa Island, there they are, same rocks from the same floodplain before it was all broken up. Let's see, we count all these islands, all 8, but we also I count the Palos Verdes Peninsula as an island. The LA Basin would look probably a lot like this, a big deep hole in the ground, but it's completely filled with sediments that are coming off of all these mountains. Another set of rocks that the islands and the coast share is the Monterey Formation, and that's full of good geologic stories, so let's pay some attention to it. This is at Goleta, and all the cliffs all along are made of the Monterey Formation. It's a really pale, fine-grained rock, and it's also very thin-bedded. So it's very distinctive, and we see it all along the coastlines and elsewhere. You've probably seen this cliff. This is on the northeast side of Santa Cruz Island, and that's Monterey Formation, top to bottom. Same stuff. Here's the Monterey Formation at Arroyo Beach, and it's the same thin-bedded, fine-grained, pale-colored rocks. You can see since it's thin-bedded, it's really easy to fold the beds, and so they're often full of kinks and folds. When you look at the Monterey Formation, it looks just kind of like mud or silt, but in fact, it's much more fun than that. If you had X-ray eyes, you could look in here and this is what you would see. These are all the shells of little microscopic plants called diatoms. In this time, the water was very rich with them, and they rained down and piled up on the seafloor. Here's another cliff on the north side of Santa Cruz. And you can see, here's the Monterey Formations, all those thin beds, and they got deposited on top of the old lavas. There's more to this story, though, because every diatom was buried with its blob of organic material. And if you bury it and heat it up, it gets converted into oil. So the Monterey is actually the source of most of the oil in our region. You can often see it just seeping out of the cliffs, and all those blobs of oil on the beach, that's natural seeps coming out of the Monterey. This is a little movie I made to talk about this. This is a cross-section north to south from Carpinteria to Santa Cruz Island. And if we could look down in, we would see, here's the Monterey Formation, this very light color. Remember, it's being squashed and shortened, that whole piece. And so all the beds of sediment that were in there have all been folded and wrinkled. This cross-section was made from studies by the oil companies of what's underneath the water on that profile. And here it is, there's a big fold there. And if we look closely at that, we can see how this works. We can see that the oil that's coming out of the Monterey Formation and the next one up actually floats on the groundwater that's in the pore space of the rocks. And whenever it runs into a clay layer, that's what these are, that's impermeable, it collects right under the fold. You've seen the evidence of this fold. It's a two-dimensional fold, like a big fold in the rug. This is a view from La Cumbre Peak, and you can see the oil rigs, these dots, are all in a line. They're all along that fold. And when you take the boat out, you can really see that. There's a point where you can see they're all lined up, slurping the oil out of all those little catchments in the fold. See, the last thing I want to talk about is ice ages and sea level changes and what that does to the landscape. This and the next figure are probably the most important figures in this talk. What I'm trying to show you is that the coastline is quite arbitrary where it happens to be located. Here's the edge of the continent. This is the continental shelf. And geologists would say that the continent ends here. The location of the coastline just depends on exactly how deep the ocean is. If you make it a little bit higher, coast will go way inland. If sea level's a little lower, like during the ice ages, it can be all the way out at the edge of the continent. This is a movie I made just to get everybody to realize how the last ice age looked. This is the meltdown at the end of that ice age. And all of Canada was covered in ice. And then it melted away and melted and melted. And as all this ice, miles deep, melted, all the water poured into the ocean and filled it up. So it was higher. Wish I could show that movie to everybody, because we all know that there were ice ages, but we don't have a very good image of how they were. This is a plot showing all the ice ages in this ice age that we're in, starting at 3 million years ago. You can see this is a proxy for sea level. So sea level was higher and lower and higher and lower every time you take the water out to make the ice or melt it, you put it back in. You can see in the earlier times, the ice ages were not so big and they were much quicker. But in the last million years or so, they've lasted a lot longer and they were a lot more intense. This little part is the last part, the last 300,000 years. We were just looking at this melt back right here when sea level fell back up. But you can see ice ages develop slowly with sea level falling, and then the climate crosses a threshold and it melts back. There's the last interglacial and previous ones. Living on the coast, these sea level changes make a huge difference for us. Here's how the islands look now, but 20,000 years ago, they looked like this. All the northern islands were one big island. Coast came out much farther, right? And we never had a dry land connection to the continent, but it was pretty narrow, just a few miles. So that leads to the story that I'm sure you've heard and that you'll hear some more about the elephant swimming across and the development of the pygmy mammoths. I won't do any more of that. Here's a more boring topic from the same thing. It's the formation of marine wave-cut terraces. So this is the campus at UCSB, and it's built on a terrace. So here's how the terraces are made. This movie is just about what we all know, that ordinarily the waves just throw the sand around. The sand is our great friend because it uses up all that wave energy. But sometimes in the winter, when there are very big waves, it picks up all the sand and drops it offshore. And then it goes to work on the cliffs. So all the big cliff erosions we have usually happen during winter storms when there's no sand to be our buffer. I made this animation with the help of some surfing teenagers. So, of course, it takes more than 2 or 3 waves to make a landslide, but boink. Here's that same picture, the University of California again, and this is all solid rock. The sand has been removed. This is the middle of winter. And now every time the tide comes in, the waves work on the cliffs. And in the time I've been at UCSB, about 30 years now, these cliffs have all landslided several times. So this was some years ago. There was a fence along and a lot of the fence has fallen in by now. One other thing that's going on along our coast is that parts of it are being uplifted. This is putting it all together. So sea level's going up and down, fast up during the meltbacks and slow as the next glacier grows again. And wherever it pauses with respect to the land, it cuts a notch, cuts that terrace and then if we're in a place where the land is rising, every time sea level rises, it'll cut a new notch in a new place. And then that that cut will be lifted up. And when that rises again, it'll cut a new one. And the result is that you can get a whole flight of stairs of these marine terraces. And they're really common to see around the islands. Here's at that same beach at UCSB. This is Monterey Formation, and this is all sand dune sands that collected on top. And when you look closely right there, there's all the shells that were living on the platform that was cut by the waves into the cliff. You can see the same thing on the islands. Anacapa Island, you know, it's all flat topped. That's just an uplifted terrace. And here's on Santa Cruz, Scorpion is just over the hill there. All that flat surface that was cut by waves when this was at sea level. Here's the west end of Santa Cruz, and you can see, let's see, there's an uplifted surface right there. Here's one that's higher and higher, higher and higher. As you go up, these have been up in the air a lot longer, and so they're much more softened and eroded. The Palos Verdes Peninsula, I told you, I view it as an island. And this is a photograph from 1954 of the Palos Verdes Peninsula before anything was built there. Now you know there it's all covered with houses and things, but look at the terraces. Wow, it's really been popping up. So each new high stand of sea level has cut a new terrace. Now this is all covered with houses and trees and things, so it's harder to see. But the people who live there actually talk about, oh, I live on the 3rd terrace or the 5th terrace or whatever. And another place where it's really good is on San Clemente Island. And you can see them. This was a wave cut surface, cliff, wave cut surface, beach cliff, wave cut surface, beach cliff, etc. It's San Clemente Island is famous for these uplifted terraces. Let's see, that's what I have for you. Thank you so much for doing this work to help humankind realize what a beautiful planet we have. These animations and many more than the ones I showed are available for download and use any way you like. There's my website, or you can find it just by typing in Atwater Animations. If you want to get your hands on your own laminated rotation model, write to me at my email. Here it is, and I'll help you get one. Thanks. I'm sorry that I'm not here to answer questions, but if I were, it's almost guaranteed someone would ask me about the Torrey Pines on Santa Rosa Island. So here's my harangue about that. There's a big forest of Torrey Pines here on Santa Rosa Island, the only other place that these pine trees exist on the earth at present is at the Torrey Pines off San Diego. You get off the boat at Santa Rosa and turn left and start walking. Pretty soon you're going along this road. You can take one of several trails that go up through the forest. The trees are quite beautiful, and they have really amazing pine cones and huge numbers of them. There's a story around that the Torrey Pines rode out on the rotating transverse ranges. Unfortunately, it's not at all true. You can tell from the genetics of the two groups that they were split apart very recently, geologically speaking. And furthermore, but during that 20 million years, the island was probably mostly underwater. The whole first part of the history is the ground is being pulled apart and thinned. And we can see Monterey Formation on tops of lots of places on the islands. Really looks like it was submerged until the latest collisions when everything's been pushed up. So forget that about the Torrey Pines. Too bad, it was a cool story. It turns out these pine cones have really big, delicious pine nuts in them. I bet they came out in a canoe, and maybe a few got spilled on the ground and got this forest going on Santa Rosa.